In the last video, we saw why we might care about linear differential equations. That is, differential equations model the universe, and if they happen to be linear, then we'll be able to solve them and understand them pretty well. So what do we mean by linear? Let's get into that in more specifics. So we're going to start with the most basic differential operator we can think of, which is just taking a derivative, right? So we know that the derivative distributes over addition, and you can pull scalars out of it. That means that it's linear, right? So we're going to think of the derivative as a linear transformation from the vector space ck to ck minus 1, where the ck is just the functions that have k derivatives and they're all continuous, and then ck minus 1, you have one less derivative, right? Having taken one derivative, there's one less to go around. So that's a linear transformation. Now, we can build other linear transformations from it. For example, we might take a derivative and then multiply by x. We're going to denote that by x times d. And let's check that that's in fact a linear transformation. Actually, there's really nothing special about multiplying by x. We could have multiplied by really any function of x that we wanted to. We'll write that a of x times d. Now, the thing about linear transformations is that if you add two linear transformations together, you should get another one. If you compose linear transformations, you should get another one, which means that we can write down just with these building blocks, just multiplying by functions and taking a derivative, we can write down a really large class of linear transformations from functions with some derivatives to functions with maybe some other number of derivatives. The most general way to write that down is this. So this linear transformation that's written as a sum of some function times taking n derivatives plus some other function times taking n minus 1 derivatives, etc., all the way down to multiplying your given function just by another function. That's a linear transformation. We're interested then in equations of the form Ly equals f of x. All right, so that f is our non-homogeneous term. It's sort of the constant term. So that's the question, is can we solve those? I want to make one observation here, which is that our entire setup for trying to solve these involves first solving the homogeneous problem. So let's go ahead and think about what the homogeneous problem looks like. Now, as we usually do when we have a homogeneous equation, a homogeneous algebraic equation, as opposed to a differential equation, we look at the coefficients and we can try to divide through by at least one of the coefficients, right? Where if we divide 0 by anything, we're going to get 0 back. So let's do that, and we'll do that with the leading coefficient, this a naught of x. So in general, that's a function of x. Whenever you divide by a function of x, you got to be careful that you're not dividing by 0. So we're going to make the assumption that this leading coefficient, a naught, is never 0. If that's true, we can divide by it. Now, if we really were being careful, what we'd want to do is to rename our coefficients. And so we don't want to write something like, call this term maybe b1, this term b2, etc. But in practice, we just assume that a naught is equal to 1, so dividing by it has no effect, and we leave the a1 through an alone. Now, how nice an equation this is, L of y equals f, sort of depends on how nice the coefficients are. These functions a1 through an, these are called the coefficient functions. We're going to assume that they're all continuous. In that case, we say that the operator L is regular and that the equation is regular. The nice thing about regular equations is that we can solve them. So that's the following theorem, which is known as the fundamental theorem of linear differential equations. This theorem says that if you have a regular equation with a continuous right-hand side, then the initial value problem that you get by assuming that y solves the equation and also telling me at a particular point x naught what all the values of the derivatives are up through order n minus 1. So I tell you the value, y prime, y double prime, etc., all the way up to n minus 1. That's say 1 less than the degree of the equation. That has a unique solution. In other words, another way to think of this is saying that if I tell you n numbers, then I've determined a solution. If you think about that for a minute, what that means is the space of solutions, morally speaking, ought to be n-dimensional. I only have to specify n numbers to tell you which solution I'm talking about. In fact, that's precisely the case. So what does it mean that the set of solutions is a vector space of dimension n? One way to think of this is, we're looking for solutions, right? So let's say we found one. Okay, then we found another one. Then we found a third one. For some differential equations, you could just sort of keep coming up with solutions, and you sort of want to know, when should I stop looking, right? When have I got all of them? What this corollary says is that once you've found n solutions and you verify that they're linearly independent, you can just stop looking. So let's do an example of that. So let's solve this equation we got from Hooke's law. Here I've rewritten k over m as c, and I want to solve the homogeneous version. I'm going to assume that c is positive, because that's the sign that we had before. You can see this thing is second order. To check that it's linear, let's see if we can rewrite it in the form that we've been rewriting it. That'll look like this. So you can see that it's just d squared plus a constant, right? Constant multiple, and we know that's linear, so we're good. This is second order, so the solution space ought to be two-dimensional. What we're going to do is find two solutions, and we're going to verify that they're linearly independent from each other. The first solution I'm going to call x naught, and that's just going to be cosine root c t. You can verify, if you pause the video for a minute, that satisfies this equation, but I'm actually going to go ahead and compute the derivatives of this thing. And I want to check one thing, which are the values at the point 0. Okay, so this is sort of looking at that fundamental theorem of linear differential equations and saying the values there as a second order, so I go up to just first derivative, and I compute the values at a point which I picked, which happens to be 0. Okay, there's one solution. Let's find another solution. So if it works for cosine, it'll probably work for sine, and we can verify that. Let's go ahead and compute the values of x1 at 0. Okay, there we go. Now the utility of having computed those is as follows. We need to check whether two functions are linearly independent, so we should compute their Wronskian. Now in general, when you compute a Wronskian, you're going to have a function, in this case of t. So instead of computing the Wronskian as a function of t, if we just evaluate it at 0, we get root c, which importantly is not equal to 0, unless c was 0, but that's a different equation. That tells us that these two functions are linearly independent. Now we know by this corollary that the solution set, that is to say all of the possible solutions that satisfy this Hooke's law equation, have to be two-dimensional, and we found two linearly independent solutions. That means we can quit looking. Any other solution has to be a linear combination of these two. In particular, that means that we can write any other solution as something times x naught plus something times x1. Let's go ahead and fill out what x naught and x1 are. If you think about the behavior of these two functions, sine and cosine, they both have this oscillatory behavior, sinusoidal behavior. They're 2 pi periodic, etc. What does that tell us about any other solution? It says, well, if you're modeling the motion of a spring, what you should look for is bouncing, right? Springs bounce. That's what they do. We've just proved that mathematically, which is good because that matches up with our understanding of how springs work.